Welcome to this tutorial. I fly in last night, arrived in the hotel about 2 p.m. or 2:30. So I know lot of people, you may experience a flight cancel and flight delay, arrive in the hotel very late in the night. So I appreciate everyone get up and come to this tutorial. Quick introduction to myself. I'm Luke Huan, published on the Huan. I just go by Luke. I'm a professor at the University of Kansas. At the same time, I work for National Science Foundation, U.S. National Science Foundation, in the directory called Computing and Information Science and Engineering, working in the division called the Information and Intelligence System. So I handle programs related to big data. Therefore, today we are going to talk about, however, on the other side is that my talk is purely representing my own research ideas. I'm not representing the foundation. So everything I said is based on my own research. So today we are going to trying to bring everyone's attention to a very important topic. I think very important topic is the safety of data analytics. So I'm going to give an introduction. In the introduction, I will just briefly talk about the general concept of data science and what is safe data science. And also, in the later half of the introduction, I quickly go through a number of programs that within NSF that supports data science. So, if you are graduate student thinking about finding a tenure track position, or if you are, early stage faculty members, you will find those information useful. And even if you are not interested in to obtain funding, knowing those programs still give you some information about the research that we support at the NSF. So after the introduction, we will have two separate topics. One is transparent and interpretable data analytics. Another one is field data analytics. So that are given by two other people. One is Shelley Lee. She's a PhD student at the University of Kansas. Another one by Chao. He is a assistant professor at the University of Wyoming. And if you have any questions during the presentation, feel free to interrupt me. And this is supposed to be a more interaction rather than just a presentation. So because I'm coming from US and also I work for National Science Foundation, so I talk a little bit about the US national priorities. And data science is highly related to US national priorities. So this relate to understand the brain, relate to critical infrastructure, relate to natural resource management, relate to health and well-being, advanced manufacturing, cybersecurity, education, and workforce development. So data science is highly related to all these topics. In industry, there's something called a hypercycle of technology. This is compiled many years ago, and at that time, we start to see data science, big data, on the exponential growth phase of technology. So basically the hypercycle, the idea behind the hypercycle is that for any technology at the beginning, first it experiences exponential growth phase. So basically it attract attention from the society. At a certain point, people start to ask whether this technology really provides benefit to the society, whether this technology really provide additional values to the customer. So this is basically the quick critical evaluation phase, and then we start to see problems. So for certain technology, eventually they resurface because they do have people do find values or real applications of this technology, and eventually they become incorporated into the daily life of our society. For those of people has been here for a long time, voice over IP. My favorite example of technology go over the Death Valley is voice over IP. When I was a graduate student many years ago, voice IP is a hot topic. And people are very excited about it. How do we, if they have this vision, if we can deliver voice over internet, that will dramatically reduce the cost of calling each other. And now it's become reality, because most of the voice now actually carried over internet, and the cost is very low. So basically, the phone company doesn't charge us based on the voice, but based on the data. So 2014, we start to see data science again, still in the exponential growth phase. And we see people very excited about that. And the KDD, I think that the KDD conference also experienced a fast growth. And some of the people attribute the fast growth to the intensive attention of people or the society to the topic of data science. So this is latest 2016, and we also see so the data science, big data, and machine learning remain on the tip. On the other side, we do start to see problems. There are several cases, and I'm not going to go to the details of the cases, but I do want to mention that. We started to see problems associated with the data analytics. Although it's widely used, we start to see security issues, we start to see privacy issues, we start to see how do we interpret these results. And I think that will continue. Those problems will continue to pop out. So that's the reason we wanted to offer this tutorial. We're trying to put the information together and talk about what we can do. So if we look into the future, this is something called the Big Research Ideas, published in Science by National Science Foundation, U.S. National Science Foundation. The idea is that NSF, the idea behind this big idea is NSF trying to say, what should we invest in the next 5 or 10 or 15 years? So NSF lists out 6 big ideas. This is related to research. For example, polar science related to studying the universe, and things related to biology, from genomics to proteomics. How do we see the information transform from genome to the what you can observe? So I would say at least 4 are related to data science. One is quantum computing. How do we develop the next computing infrastructure? And for biology, genome to genotype to phenotype, that involve a lot of data. And here, of course, big data, harnessing the data revolution is one of the big ideas. And another one is the human technology interface. Actually, I like this picture a lot. So basically, it's very visionary and forward thinking. Let's imagine 5 years down the road, what will happen? Well, we are going to see like an automatic car. So driverless car driving will become reality. So it is becoming reality. We are going to see cars that are driving by itself in cities. And then when you use app like Uber or Lyft, you may have access to a car that's driving not by a human being but by a computer. On the other side is the CyberPhysical Systems. So basically the sensor technology connecting all the buildings, all the infrastructure together. So when you are, for example, when you are 100 meters away from your office, maybe your office air conditioning will be turned on. And when you are like less than 1 mile away from your home, then depends on the programming. Maybe the first air conditioning in your home is turned on, then light is turned on, and then you start to automatically bake things for you if all the things are in place. And also wearable devices. Wearable devices are monitoring your health signals all the time. For those people may have certain tendency to high risk diseases like a heart attack. So those sensors monitor those signals and give warning messages to those people. And also your investment, there. So now is people are managing your bank account and also your investment, but 5 years or 10 years down the road, maybe most of them will be managed by computer softwares. So imagine, so that will bring a great convenience to the individual, right? So there's a driverless car driving. Everything is monitored by sensors, and those sensors are connected by each other, and they're intelligent component behind all these things that are based on the data, trying to make a decision for you. But there's a lot of problem. So if we think about the security concerns, now if we have people trying to hack a car and be a human bomber, they only have control of one car. But if we have this driverless car driving, one person if once they gain the control, they can control hundreds of cars or thousands of cars and launch an attack to the society. That will be a very serious concern. And also think about this automatic for your investment, high frequency trading. This last year this movie related telling a story that there's a company doing high frequency trading, and there's one day they lose the couple of $1 million, and everybody is just asking why. And also think about your health. Right, so basically the software is monitoring all the data and also trying to assess your health state. Well, what if there's a glitch? What if there's a problem in the software, and you trust it so that your health state are monitored? But what if all these are based on data, and if we don't fully understand the mechanism behind the data, can you trust it 100%? So that's what I want to mention at the beginning. What are the safety issues? And of course, recently the NSF released a bunch of Dear Colleague letters related to data science, not related to the safety, but related in general the data science part. For example, one Dear Colleague letter early in this year is trying to federalize the sources of data, trying to put the data into a centralized place so that the research community can start to study that. Another one reason, the one related here, is convergence. So basically the idea is that the data science is penetrating into virtually many disciplines in the society. Then how do we encourage those interdisciplinary research and truly develop a solution to one discipline? And also there are international collaborations. NIH recently, I think 2 months ago, released this call for proposal. They're trying to build an infrastructure called the data commons. They're trying to integrate the data across many different divisions of NIH. And also DARPA has this explainable AI, auditable AI, and many call for proposals that actually relate to the concept of safe data science. So before we talk about safe data science, let's talk about what is data science. Well, there are many versions of what is data science, right? There's one version that everybody talks about it. Nobody really knows how to do it, and everyone thinks everyone else is doing it, and therefore they claim that they're doing it. I don't know what they're talking about, but I assume they're talking about data science. Another thing, deep learning is very popular, right? So people think. So some people think the future of data science is deep learning. Other people say deep learning is part of data science, but not the whole data science. Nevertheless, let's look at those images. First, so what a society, I don't know whether you can read that, what a society thinks I do. Think you're threatening, you're taking the job away from people. Okay? My friends think I do is the brain with computers. And the other computer science thinks, which is not I, okay. I also think that way. So if you work in deep learning, there seems the job opportunity is high, and the company is willing to pay big packages to recruit those people. And what mathematicians think I do, mathematicians think that computer scientists using these tools developed by mathematicians many years ago. And of course, I think I'm solving the most important problem in the society, and maybe in the reality is that from Theano import all the packages. So maybe I just, at the end of the day, just use packages, okay? There's another you can find many images in this way. So there's another things about data scientists. So what my friends think I do. So basically, we write down these equations, trying to work with each other. And what I think I do, are trying to crunching numbers, 0 and 1. And society thinks what we do is that we're trying to develop a cutting edge technology. And what my boss think I do, you just plot using Excel, plot those trend, and then produce figures. And what I think I do is I go through all the MATLAB, go through equations, trying to understand the algorithm, trying to understand the math behind algorithms. But I actually do is that maybe select stuff from this table, run in SQL, put the data together, and then run in deep learning packages. Okay, so there are a lot of those things. I think this reflect that it's a dynamic growth. And we think that data science has a lot of societal connections. So that's also related to the safety concept that we are going to cover in the next few slides. If we think about that, if we think about data science, then I guess there are a few challenges we need to recognize. One is that there's a huge heterogeneity in data science. I think in the previous two slides, you already get the concept. Let me be more specific. There's one project called Earth Cube. That's a very big project funded by NSF. What the project want to do is that we're trying to integrate the data at many different observation sites on Earth. So basically, we're trying to integrate the temperature, wind speed, wind direction, all this information into one integrated database, so people can have access to it. If we look at the Earth Cube project, it has distinguished characteristics. It has a very strict requirement about the real time. So we're trying to all this data collected in real time and trying to integrate in real time and present to other people in real time, so people can build an application on top of that. Definitely the non-IID data, because different sites on Earth, the distribution clearly are different. On the other side, they are well-structured data, usually a numerical data, and then the data has a huge volume, but it's a vector data, and there's no human subjects. On the other side, if you look at the electronic health record, if you look at all these images or diagnosis or genomic sequencing data related to a patient, the data is very complex. is longitudinal data. So basically you have information related to the patient back to several years or maybe tens of years ago. Typically, other than genomics data and image data, typical electronic health records are not very large. The volume is not very large, but they are very complicated. They may involve family history, they may involve drug, disease, and also gene interactions. And on the other side is human subject data. So privacy is a very important issue. So the second part is that in accelerating science is that we need a convergence team, especially in the concept of data science. So basically, we need the people from computer science, from mathematics, statistics, and also computational science. But on the other side, we need the people understand large-scale infrastructure so that we can design algorithm, but we can also have the infrastructure to execute the algorithm. And also we need domain experts. So, and also making translational data science into reality is another challenge. So the term translational science is borrowed from NIH. That basically means from bench to bedside. What does it mean? That we do basic research, but we're also trying to connect the insight from the basic research to a real application. If we think about the data science, we think about it has a connection to many problems facing by our society: natural resource management, health, community management, smart transportation, crime justice, and education. So what are we going to see in the next few years? We're going to see a bunch of challenges. I'm going to I will in the next few slides I just present a few challenges that I feel be very important. So these slides, of course, is collected a couple of years ago, documented for each industry sector. What are total volume of data collected by each industry sector, and also for those industry sectors, how many firms have more than 1,000 employees, and also store data per company. So from this list, we can see that manufacturing they produce a lot of data, and they produce a lot of data overall. If you look at the per company, then those are security and the investment companies. They produce a lot of data per company. So, and if we look at the data types, we see video, images, audio, text. So I think a joint analysis of this different type will be very important for industry. Another part is this IoT, Internet of Things. So the sensor technology developed significantly, and the capacity of sensor become increased dramatically. The battery life is increased, the processing power is increased, and the capacity to do data analysis increased. So here is showing that number of connected nodes per industry sectors, and then showing the in terms of growth rate. So for example, we see health significant growth, security significant growth. Another very important part of in general data science, benchmarking and automation. So now we have large amount of data, and many people develop algorithms for that. But how do we compare them? I guess a critical evaluation is important. So in terms of benchmark, we started to see different benchmark at different levels. I guess that should be significantly increased. Then there are related questions: how do we find the benchmark? How do we maintain those benchmarks? Another related question is training and workforce development. So the whole field of data science is moving forward very fast. And how do we train our student in the next generation computer scientists to catch up the latest technology? So basically we see that we see a long list of courses that people are interested in. Those relate to mathematics, statistics, programming, information retrieval, data mining, machine learning, and also relate to how the data science actually interact with our society for business intelligence, for example, social science, policy, and also we haven't really talked about the applications, and also for continuing education. For people who already finished the degree, they also want to catch up. How do we provide those information? So how do we provide those services? So again, I don't think anyone has one big solution to all these problems. So I think there's those components. The components we need to think big, think really broadly, but on the other side, we need to think about small. We also need to think about the actions, and then we think about responsibilities and impacts. And that's the focus of today's tutorial. Think about the responsibility, think about the impact of data science to our society. Think about how this data science may impact people's daily life. So on the other side, we think that all the people doing data science should explore, should have access to the cutting edge technology, but also on the other side to get connected to the end user of data science, and also awareness of local constraints and awareness of discipline cultures. So let's come to the safety side of data science. So now let's look at the example. Okay, so here we have a training data, right? So I showed this bunch of images. That basically means training data. Once we have training data, we can go through a training phase to produce this multi-layer neural network. Yes, and now you can, 20 years ago, because of the limitation of computing power, you can build a 3-layer, 5-layer, 6-layer. That's probably the limitation. Now with the fast-growing computing power, especially graphics processing unit, people sometimes build a 100-layer neural network for image processing. The accuracy is very high, right? You get a prediction, and the accuracy is very high. But once you get the accuracy, you ask, if you adopt the operational view of data analysis, is all you care is that I have training data, I have a model. Then as long as my models, this is something called the generalization error. So my training error match, if I process an infinite number of testing images, as long if the error match with my training error, so generalization error is low, and on the other side the accuracy is high, I'm happy. Okay, so if you adopt the operational view of data science, then that's all you care about. But on the other side, I guess you will see examples from the subsequent discussion. You'll see examples that people are actually asking more than that. If these images are, you're trying to classify this image, whether there are those sports facilities versus agriculture field, if you make a mistake, that may not be a huge thing. If you don't fully understand the mechanism, that may not be a huge thing. But on the other side, if we think about automatic car driving, if we think about the automatic car driving, if they have a mistake, if the software make a mistake in image processing, the consequence could be a collision, and then that may lead to harm of human beings and loss of properties. And if you think about those are biomedical images, and then people are going to do a diagnosis based on the prediction of the images, right? So for sound images, if you make one mistake, from operational perspective, that's pretty good. Accuracy is very high. But if for that one image, this one person make a misdiagnosis, that means could be this person does have cancer, but on the other side, the computer misread the signal, or the other way around. So I think so. My argument, my thesis is the following: with the widely adoption of data science technologies, with the wide adoption of deep learning technologies, and what we start to observe is that those capabilities are incorporated into utilities, and those utilities have impact to human beings. And once we observe that, and those phenomena is on the horizon, we cannot deny that it will happen. It will happen. It is happening now. So in that case, as a researcher, what should we do? I argue that we should try to think about the consequence, think about the responsibility, think about the impact of those technology. We need to, for example, if we apply those technology to human subjects, we should think about fairness. And you will see a couple of examples that in the legal system, in the criminal justice, people does use data science technologies trying to assess how likely a person will recommit a crime. And when we do that, we need to make sure we don't the algorithm, the data science capability we developed is not a reinforcement of the bias in our society. We need to make the things interpretable, so that so that people can gain additional insight into what's going on. It's not just treat the whole thing as a black box. And if we get 99.9% accuracy, we're happy. We're trying to ask what happened. What does this model tell us? And we need to make the whole thing transparent, so that even if we cannot completely understand what's going on, at least we can reproduce the results. And we understand all the trade-offs we played during this model construction process. And also, if we think about cyber-physical systems, those when we have intelligent component work with a physical component, for example, automatic car driving, so we need to make sure the whole system trustworthy, accountable, and also auditable. So that's what I mean by safe data analytics. So it's a set of concepts. It's a broad set of concepts. They are related, but they are not complete. They are related concept. It's broad. And it's not just a software development. It's not like we want to develop a software so that they are reliable. They won't make a mistake. That's the scope of safe data science is definitely more than that. It's not a software glitch if we make a mistake. It could be the bias in your data set, so that when you build the algorithm, you inherit that bias in your data set. It could be when you build the algorithm, the data set may be fair, but when you build the algorithm, you actually introduce priors. And sometimes those priors may reflect the society's bias against certain groups. So basically, the message I want to get across the community is that we should not only pay attention to prediction results, but also other things. We're trying to demystify the black box, make it fair, make it interpretable, transparent, trustworthy. And also, another thing I want to bring everyone's attention to is what are the future big data analyzing platforms. So we see the great advantages in greater technology advances in database. We see every year you probably experience that thousands of papers now are published on different data analytics technologies. Hyperperformance computing and architecture. So Google released this TPUs, tensor processing unit. So we have now CPU, GPU, and now TPU. And also, I think Google is trying to provide a service to the research community and the visualization. But I think if we think about it in the future, we should have an environment that supports collaborative model construction. It should support automatic model construction and also model optimization. So the data science should become a utility that you don't need advanced training in data science. You can have access to the most recent technology advance. And it should support declarative model construction. So as a user, you don't need to worry about all the details about how to do those optimization. So you basically tell the system, I want to build these following models. I want you to optimize those hyperparameters. Then the system should be able to do that. It should support model sharing. We start to observe that, for example, different disciplines, this relates to the concept of convergence. Different disciplines actually come to the same set of models. So there are models used in biology community. Those models actually, when business people look at those models, they feel that it's actually useful for the business applications. But because of cultural difference, so people publish in bioinformatics, advanced ecological modeling, they have their own publishing value. And the people doing the business intelligence, they usually do not check out the latest progress in those publishing manuals. So we should have an environment support the model sharing. So allow people from different disciplines, they can share their experience. And also, we should make everything reproducible. So maybe we can call these things a model commons, an environment that you can share models, you can share data, you can invite other people to do analysis for your data. And you can, once you build a model, you allow people to reuse the model. And we're talking about the life cycle of the model. So you know when you may use the model, when you should stop using the model, or when you should update the model, or when you should transfer the model to a different application. I think that should be a very interesting research topic. So do we have that? We do have a few prototypes related to that concept. For example, KNIME. KNIME is provide a very nice user interface to try to incorporate different data analytics components together so that you can configure the workflow and you can launch the experiments. You can inspect the results. And Facebook, I don't have inside information about what they have, but they have a blog, so they share the information. So there's a Facebook Learner. It's supposed to be a collaborative environment with 3 components: that the execution environment, the UI to launch experiments, and many predefined pipelines or workflows for data analytics. And there's another company produce data robots, and that basically provide many of the things I described. However, if you look at all of them in details, you will find that none of them really deliver what I described in the previous slides. So again, in order to connect everything back, so first we do start to see the data science become utilities. So people start, when they're trying to solve a complicated problem, now people adopt this thinking of the 4th pillar. Like let's collect the data, let's label the data, and let's use the machine learning AI to figure out the connection. And then we can build a model, using the model to solve the complicated problem. And we start to see those utilities embedded into many applications. and eventually will have a significant impact to our society. But once in this process, again, the safety is a very important issue. You don't want your job application get rejected by a computer simply because the computer has some prior information that against you. Okay. And you don't want your loan application get rejected by the bank because they have because you're living in an area and that area considered as unsafe by the bank. There's something called a red line. And recently, the EU just passed a regularization saying the right to get explanation and the right to be forgotten. The right is to get explanation that within the EU territory, if any company or any entity using algorithm to make a decision for human subject, the human subject is subject to get the explanation.
That's not quite true. That's a bit of a misreading of the law that's been repeated in data science communities.
Okay, but I do read the article, and I think last year there's a talk on that. So maybe technically we can argue about that, but I think that's the intentions there.
I mean that's been in the law since about 1995, mostly. It's a contentious issue in the legal domain, like the paper in a machine learning workshop, which didn't really read the law in a way that lawyers would agree with.
Okay.
So it just
right. Okay. There could be some discussion on that, but I think that the people start to see the issue and the intention is definitely there. And also the reason is that the data you can be forgotten by the so that means people cannot keep your data forever, and that have significant impact to companies like Google and Facebook. So I guess. Okay. So any questions so far? Okay. Yes.
About something different.
Right.
Relating to when you just define safe.
Right.
A few things that I thought were missing from that, and you talked about fairness and transparency, were resilience and things like concept drift in practice, and also things like adversarial machine learning systems.
Yes.
Yeah. And those things, for me, when I think of the word safe, that's what I would put, at least at the top. But I also agree that fairness and interpretability are important components there. I was just surprised to see those kind of things missing from that.
So basically, we do talk about So basically, transfer learning is very important. When we build a model, it should be resistant to the shift of distribution. Originally, I do plan to have to cover a little bit on the security side, so adversary sample generation. It turns out we have enough materials for the first two topics, and I think the third topic we're still doing research on that. That's why. But thank you for mentioning that. Okay. Any other questions? Okay, so since I'm here, so my colleague mentioned maybe you can mention a few words about nation science. Let me quickly go through that, and to tell you a little bit about the programs that are related to data science. So for those of people in graduate school or early career tenure track faculty members, you will find those information very useful. For those people not interested in obtaining funding from National Science Foundation, you may still see what type of research we support. That's a useful information. So NSF basically every year we get about 50,000 proposals and issue about 10,000 awards. And that support many people across the country. So that's the infrastructure, that's the organization map of NSF, and Jim Crozer is director of the computing and information science and engineering. Within science, there are four divisions One is called Office of Advanced Cyber Infrastructure. Another one is called Computing and Communication Foundations. Another one is Computer and Network Systems and Information Intelligence Systems. So what are they doing? Office of Advanced Cyber Infrastructure support the development, acquisition, and also provision of infrastructures that support all different types of computer science research. CCF supported the software and hardware foundations, so support the algorithms, supported the architectures. And then CNS supported computer science system research that's related to, it could be related to the single computers, it can be related to networks. And also information and intelligence systems, basically trying to, we study human factors, intelligence, and data. So basically here is a statistic showing that for academic basic research within U.S., for National Science Foundation, what a fraction of the academic basic research actually supported by National Science Foundation. For computer science, NSF provides more than 80% of the funding supported the research for all people in that research community. So let me go through a few programs. One is that if you're interested in infrastructures, if you want to do big data research, you say, I don't have access to 8,000 core computer. What can I do? One is that there's something called the CRI, Science Research Infrastructure, that give grant to people want to do research specific in computer science. So you can purchase hardware, you can purchase cloud computing hours. If you want to do research about how do you construct the advanced computing infrastructure, so you can submit there's a program called XPS that to support the research about how to advance parallel computing for many different applications. And for those people in the early stage of the career development, for example, for tenure track assistant professor in the first 3 years, then you can submit you say, I have a startup package, but it's limited. I can only support so many students, but I want additional resources. So there's a computing research initiative, CRII, so that enable people to do the transition. And algorithm in the field is a program that support the research on algorithms in many different applications, including data-intensive application. Expeditions in computing, those are really for senior people, like there's a $10 million or $20 million in 5 years for significant, very visionary, forward-thinking problems at the frontier of computing. So then we have programs that are not only within computing and information science and engineering. It's called cross-directory programs. Those may cross multiple application areas, and those related to, for example, the computing plus STEM education, and the smart and connected communities. Those are the smart and connected community are launched last year. So they basically enable the overall using computing to enable sustained change to enhance community. And the smart and autonomous system is another program launched last year. The idea is that to do research to advance the intelligent physical systems, including automatic car driving. And the big data, of course, is a part of the is a program that cross many different directorates within NSF. So you can do research using big data to advance health. You can do research using big data to advance social sciences. And then big data regional innovation hubs. Those are the ideas that bring industry, research, and also application together so that people work on big data will have access to the problems that are interesting to industry and also have access to problems in different disciplines. There's a SAT-C, a secure and trustworthy cyberspace. So the relate to security and privacy. And SI2 is a program support large-scale software development. So basically, if you have a program if you have a software that already being used by the community for a number of years, and you want to push it to the next level, you can obtain support from that program. And then we also have NSF also work with other agencies to promote research. So I just select a few ones that relate to data science. Really. So for example, the BRAIN is a project that involves many federal funding agencies that are trying to understand the mechanism and the functionality of brain. And the collaborative research in computational neurosciences, that's as part of the BRAIN project. So NRI National Robotics Initiative is involve NSF, NIH, and DARPA and other funding agencies, basically doing research related robotics. And the smart and connected health, that's between collaboration between NSF and National Science Foundation. You're using data science, using computing to advance research related to health. And the CyberPhysical Systems, that's basically, that's also involved many funding agencies, is incorporate computing, communication, and control, including data science in physical systems. So if you're interested in that, if you're interested in what are the research supported by U.S. National Science Foundation, you're interested in getting the latest information about the programs, you can, there are Twitter message, Twitter, you go to NSF website, you can visit, you can subscribe to the email, and also there are Facebook, there are Twitter messages, there are many different social mediums, you can get the latest information. Okay, so I want to thank University of Kansas and National Science Foundation to support my work. And with that, I conclude the first part of the talk. Any questions? Okay, then we're going to do a shift. So Xiaoli Lee, she is a PhD student at KU. She was going to talk about transparent and interpretable machine learning.
Today I'm going to talk about transparent and interpretable machine learning. First, I'll give an introduction about why we need transparent and interpretable machine learning through several examples. Then we will investigate transparent and interpretable machine learning from 5 aspects: concepts, definitions, metrics, algorithms, and applications. First, as everybody has noticed, machine learning has been widely applied to different real-world applications, including some applications which may have significant social effects on users, such as medical diagnosis, intelligent tutoring system, personality prediction, and marketing analysis. And you may wonder, since the success of machine learning has been demonstrated in various fields, so why we need to put extra efforts to develop the transparent and interpretable machine learning algorithm? To answer this question, let's first see the difference between traditional machine learning and transparent and interpretable machine learning. In traditional machine learning, usually the algorithm or trained models are often opaque to users. We don't know the underlying reasoning process of that algorithm or models. Given an example, we will have the prediction, but we don't know how the prediction is generated, why we get that prediction, which feature contribute most to that prediction. And if we change the inputs, how the prediction will change. And a large number of machine learning algorithms fall into this category, such as SVM, deep neural networks, and random forests. For the transparent and interpretable machine learning, it added 2 extra dimensions to the traditional machine learning. The first dimension is who. That is, who needs transparency and interpretability. They may include data scientists, domain experts, and affected users. The second dimension, the TML as to the traditional machine learning, is what? That is what type of or what kind of transparency or interpretability that the TML try to provide. We may want to understand something about the training data. That is how the data is collected or pre-processed. Or may want to get some transparency about the model itself. We may ask how the model is derived and what it is doing. Or in the prediction, we may want to know how the prediction will affect the individuals. And what does the prediction mean to the affected users? Has seen the difference between the traditional machine learning and the TML. Now I would like to present several examples to see why we need TML. The first example is from pneumonia risk prediction. In the work proposed by Caruana in 2015, they describe a model. It will assign lower risk to those patients who has asthma. The reason is that those patients have received more aggressive treatment due to their asthma. But now suppose we are training a complex model using the same training data. Due to the high complexity, it may be very difficult for us to know there is a pattern in the training data that has asthma will lead to low risk. Then if we blindly apply this model to a situation where those patients has asthma, but has received no treatment at all or less aggressive treatment, then it will be very dangerous. Another example is from social network. In 2014, Facebook introduced a new feature. Why am I seeing this ad into Facebook? Nowadays it is unavoidable to see advertisements when browsing websites. Sometimes you may feel annoyed when you see an ID you don't want to see. You may feel that your privacy is violated. So this new feature introduced in Facebook may help to alleviate this problem. To be or not to be may be a big problem, but to see an ad or not to see an ad may be a trivial. We can just choose to ignore those ads we don't want to see. And it's optional for websites to provide explanation or not. But for some decisions made by machine learning algorithms, they may have significant effects on users. We may wish that we have the right to ask for an explanation. In fact, maybe there are some arguments about this EU regulations, but I still want to present it here since it published in last year's ICML workshop by Goodman. He's from University of Oxford, and the EU adopted a set of regulations about the right, the right to explanation, so that the user can ask for an explanation about some algorithmic decisions made about that. You may ask, do we really need this kind of regulations? Hopefully, this example from judicial decision-making can give you an answer. Recently, a Wisconsin man, Mr. Eric Loomis, was sentenced to 6 years in prison based on risk assessments from a private company's software. Based on that software, Mr. Loomis has high risk of violence, high risk of recidivism, and high pretrial risk. But since that software is proprietary, And this will prevent Mr. Loomis or his lawyers to challenge the accuracy or scientific validity of the assessments. So he felt that his right to due process was violated. And Mr. Loomis appealed his case to the Wisconsin Supreme Court. This example is about deep neural networks. You may already have known that deep neural networks have been widely applied to image recognition due to its near human level or even superhuman level performance. But it's only one side of the story. The other side of the story is that deep neural networks can also be easily fooled, like we showed here. There are 4 images in the figure. For the right 2 images, it is not surprising that a state-of-the-art deep neural network will classify it correctly with high confidence. But it is surprising that for the left 2 images, it will also classify it as guitar and penguin with very high confidence. So the deep neural network has made some unexpected mistakes. It may fail unexpectedly sometime. Then if we don't know the learning mechanism behind an algorithm, we don't know how the prediction is generated, why we get this prediction, it may be problematic if we deploy a deep neural network to an adversary situation like this. The last example is about the collaboration between domain experts and the CAD systems. The recent studies show that when radiologists and CAD systems work separately, they will achieve better performance than they work collaboratively due to the distrust or lack of understanding. The problem may be solved if we can provide an explanation for each specific decision made by CAD systems so that the domain experts can know when the model may fail and can have a sufficient understanding about the decision process of the CAD system. Their trust on the CAD system may be improved. Have seen several examples of the reason why we need TML. Now let's summarize it through the first dimension of TML, that is, who needs transparency? For individuals, they are entitled to ask for an explanation if those algorithmic decisions made about them will have significant effects on them. For domain experts, they may want to understand when the model may fail and when they can trust it or not trust it. And so they can critique the models. For the organizations, they may need to provide justifications for those user-level predictors to avoid discrimination. And in addition, they can minimize the risk brought by the decisions made by algorithms. For data scientists, they may want to understand the transferability of the model so they can know when they can safely apply a trained model to a different situation. In addition, they can find some unexpected patterns in the data. That's the first part of this talk. Now let's proceed to the second part. And we already know the reason why we need TML. But what is TML? How do we evaluate the transparency and interpretability? And what kind of techniques we can use to achieve transparency and interpretability. And lastly, what kind of applications we can or we should apply TML to them. First, let's see the properties and the concepts of TML. First and most importantly, TML is not a monolithic concept due to the following two reasons. As we mentioned before, TML as an extra dimension to the traditional machine learning, that is, for whom we are trying to provide transparency and interpretability. So one property of the transparency and interpretability is that it is subjective. The transparency and interpretability may be related to a user's prior experience or knowledge. For example, a decision tree may be transparent to a data scientist, but not to a layman user. Secondly, the other property of transparency and interpretability that it is context dependent and can be defined in different levels. We may want to have understandable predictive models or understandable algorithms, or even the adaptability of those models. Then what is exactly transparency and interpretability? In Lipton's work, published in 2016, they define transparency as how does the model work, and interpretability as what else can the model tell me. So they distinguish between transparency and interpretability. But for the considerable amount of work in the literature, transparency means interpretability and vice versa. In this tutorial, we will not distinguish between transparency and interpretability either. As we have mentioned, since the transparency and interpretability can be defined in different levels, so in the literature, different definitions of transparency and interpretability has been proposed. We summarize them in those four groups. That is transparency, interpretability in outcomes, transparency, interpretability in models, transparency, interpretability in model operations, and transparency, interpretability in modeling processes. For the first group, they define transparency and interpretability as that the model has the ability to explain its reasoning process. They can provide explanations for their predictions. For the definitions in the second category, transparency and interpretability is defined as the model structure, model behavior, or the internal states of those models can be inspected or visualized. For the definitions in the third group, transparency and interpretability defined as sorry, I missed out the first and the second group. The definitions I mentioned before in fact, are the definitions from the first group, from the second group, from the third group. And for the definitions in the second group, and they define transparency and interpretability as the models are simple and easy enough so that a human can understand and they can contemplate it at once. And for the last category, here transparency and interpretability means that the construction process or the modeling process of the model affords explanation. Now we come to another topic, that is how we can measure interpretability and transparency. Since we have different definitions for interpretability and transparency, so we need different metrics to evaluate transparency and interpretability. The first metric is that we may evaluate transparency and interpretability by human experts, since transparency and interpretability is subjective. The second type of metric we may use are complex measures of those models. For example, the sparsity, the number of nodes and depth in a decision tree, or number of rules in a rule-based algorithm. Another type of metrics we can use to interpretability and transparency is that the similarity between a model and a standard interpretable model. For the categories of TML algorithms, we also divided it into 4 categories based on the second dimension of TML. That is, for what kind of or what type of transparency or interpretability we are trying to achieve. We may want to achieve transparency or interpretability in outcomes, in models, in model operations, or in modeling processes. In the following, I will present those algorithms in these categories one by one. First, let's see transparency and interpretability in outcomes. Basically, those algorithms from this category try to explain the predictions or the underlying reasoning process of those algorithms through various texts. The first method we are going to present is from the work proposed by Hypercycle in 2016. That is in last year's KDD. Why should I trust you? Explaining the predictions of any classifier. They proposed a method to explain the predictions of a model by quantifying the contributions of each features as illustrated in the figure. Here, the task is to determine a document is about Christianity or atheism. In the figure, those most relevant words are listed. For each word, there is a bar corresponding to it. The color of the bar indicates which class that word contributed to, and the length of the bar indicates how much that word contributed to the predicted label. Through this technique, then we can know which features are most influential for the predicted class. For example, in algorithm 1, we can see that God and mean contributes most to the class atheism. Different from this technique, Kim proposed a method to explain the outcomes through 2 types of examples. Prototype examples, they are data points that are most representative of the class, and criticism examples, they are data points that cannot be well explained by the model. In the figure, we show 2 types of dog breeds. The first row are prototypes. You can see that those pictures have very typical dogs. And the second row are criticism. They picked out those pictures are very hard case for the classifier. For example, dogs in costumes, dogs in movements, or dogs with different coloring. The third kind of technique we're going to introduce is that they try to explain the predictions through auxiliary information. In the work proposed by Ring, they introduce a method to incorporate anchor terms provided by the domain experts to guide the discovery of latent topics. The table shows the results from two methods. The results in the first row didn't use anchor terms, and the results in the second row use anchor terms to discover latent topics. From the results, you can see that those topics discovered by using anchor terms are more coherent. And in addition, those anchor terms provided by the domain experts enable the discovered latent topics to be interpretable. That's the algorithms in the first category. For the methods in the second category, that is transparency, interpretability in models, the strategy here is to try to construct models with low complexity. To achieve this, one kind of technique is used to use supersparse linear integer models. These models can incorporate constraints for interpretability and transparency into the models seamlessly. For example, in application to sleep apnea screening, it is required that at most 5 features can be used in the model so that the model to be simple enough and other physicians can understand or explain the model in a short period of time. Another kind of technique used to construct low complexity models is generalized additive models. They try to reduce the complexity of the model by excluding complex interactions among the features so that the user can understand how each feature contributes to the prediction individually. The third type of method that has been used to achieve low complex model is to use rule-based interpretable methods. For example, Lacroix has proposed a method for the interpretable decision size. In this model, they don't use a hierarchical structure, and the order of the rows doesn't matter. So the model can be easily understood. For the methods in the third category, to achieve model operations, they usually will inspect the dynamics between the input and output. The first algorithm we're going to introduce is proposed by Cross, and they develop a method to visually inspect the dynamics between input and output using the partial dependence. The idea of partial dependence is illustrated in the figure. In the rightmost image, we listed a number of original samples and their predictions. In the leftmost two images, when we change the value of glucose, we can see the predictions of the risk also changes. So that we can know that how the changes in the feature values can affect the predictions. To visually inspect the deep neural networks, a method has also been proposed by Usinski in 2015. As shown in the figure, in the middle of the figure, they plot the activation values of those neural units in a layer of a convolutional network. And the green box denotes the selected neural units or the selected channel we may be interested. And from the figure, we may notice that the activation of the selected channel is caused by the face of the cat, like we showed in the select channel here. The other type of techniques we try to we can use to achieve transparency and interpretability in model operations is through failure mode prediction. In Benson's work, he proposed a method to predict when the model may fail by clustering those samples which cannot be correctly classified by the model into different clusters, and each cluster corresponds to a failure mode of a model. And each cluster has a semantic characterization. Here we show the images from the different clusters. And each row of images are from the same cluster. For example, for the image in the third row, they are from the cluster. Also, a failure mode of that model. It has a characteristic that it is small and it is not strong. Different techniques has been proposed to achieve transparency and interpretability in model operations is to review the internal states of the trained models. Specifically, that model will first select those internal states and the users may be interested in. Then it will inspect how those internal states of that model will change by interacting with the machine learning process, by changing the internal parameters or adding new records to the model. For the models in the last category, that is, we try to achieve transparency and interpretability in the modeling processes. The first algorithm we are going to present is that they try to construct a model by provide a natural language description of the construction process. And they also constructed that a complex kernel through a set of simple and easy to understand kernels. The second strategy we are going to present here is through constructive learning. That is our work. It will be published in this year's KDD. We are trying to achieve transparency and interpretability in model construction by asking the following two questions. First, how the model is incrementally constructed. Secondly, when and why a model needs to be updated or modified. To answer these two questions, we rely on constructive learning, that is a human learning theory about how human knowledge is incrementally constructed. There are two key processes in constructive learning. First is assimilation. It will incorporate new experience into an existing knowledge framework without changing that framework. The second process is called accommodation. It will change the internal representation of the external world when we want to incorporate a new experience into our existing knowledge. We may see these two processes through an example. When you see this dog, you may already have knowledge about this dog, and you can immediately recognize it. And you don't need to change your existing knowledge, so it corresponds to the assimilation. But when you see this animal, you may wonder what it is, where it is from, and then you need to construct new knowledge for it. That is the process of accommodation. Based on this human learning about how to incrementally construct new knowledge, and we proposed a new machine learning paradigm. In this new machine learning paradigm, we assume that those samples will arrive sequentially. When each new sample arrives through constructivism learning, we will either assign it to an existing task if it can be well explained by that task, or we will assign it to a new task if we have sufficient evidence to believe that there is a new pattern in the data. Have introduced the algorithms in different categories. Now let's see what kind of applications TIML can be applied to. Here we list a number of applications TIML has been applied to. For example, healthcare, risk prediction, topic discovery, musical composition, and etc. In the following, I will present several real-world applications. The first application is from healthcare. Here, to achieve transparency, a decision tree is developed for risk stratification recommendation. The decision tree is just a sequence of rules. They can be applied one by one. And the ratio of positive class will increase over those rules. The second application is about the recommender systems. In Google's music recommendation system, when they provide a recommended music to the user, they will also provide an explanation for it. For example, for the first music it recommended, it explained it maybe because it is similar to Joe Hisaishi, so it will recommend it to me, since I have listened to Joe Hisaishi a lot. To achieve transparency and interpretability in image recognition, she proposed a method to visualize what the model will see when generating the image caption. As shown in the first image, when the word of frisbee is generated, the part of the image it corresponds to frisbee will be highlighted, so that we can know which part of the image that model fixes its gaze on. In social network analysis, TMR has been used to understand how the personal information provided in social network can affect the predictions or the inferences about the individuals. Here we show an example that use this figure, that how the predicted probability of being gay will change when the number of likes of a user is removed one by one. We can see this curve. When we remove the number of likes and the predicted probability of being gay will drop dramatically. By understanding this, so we can know how we can protect the privacy of the users. In robot training, TRML has also been used to make the learning process of the robot transparent to the human teachers, so that they can know the robot when the robot may are uncertain about the action selection, so that they can provide guidance messages for that robot. That's all the applications I want to present for the TRML. And also we came to the end of this part of the tutorial.